Multiplication rule. Suppose we're interested in the probability of events A and B both occurring. This is where we can use the multiplication rule, and here's how it works out. Notice that we have probability of B given A, the conditional probability, multiplied by the probability of A. So the probability of A and B both occurring is a multiplication of these two probabilities, one of which is a conditional probability. Let's look at the M&M's problem again. So we select them one at a time and eat them, so without replacement. We found previously that the probability of red on the first and green on the second given red on the first, those probabilities were here. If we're interested in the probability that both events red on the first and green on the second occur, we'll use the multiplication rule. So we're going to multiply the probability of red on the first times this conditional probability, green on the second, given red on the first. So red on the first, green on the second, given red on the first here. All right. You can also use a tree diagram that we used before. So as we saw before, this is the probability here of red on the first, and this is the probability of green on the second given red on the first. So the probability of red on the first and green is the probability of red on the first times the probability of green on the second given red on the first. Same as we had before, right? So these are all conditional probabilities on the branches here, right? So this is the probability of red on the second given green on the first. So if we wanted to know the probability of red on the second and green on the first, we'll multiply green on the first. Again, it's 28 over 110. So in this case, it does turn out that the probability of red on the second and green on the first turns out to be the same as the probability of red on the first and green on the second. Let's revisit our drug test example. We're interested in the probability uses drugs and positive test. Well, as before, we can read right off the chart. There are 45 positive drug users and 555 total. Now this is not a conditional probability. We're not assuming positive test, so we're not looking here, and we're not assuming drug user, so we're not looking here. We want to know the probability of those two events happening simultaneously. So it's 45 over 555. You can read it right off the chart. Well, let's see that that's the same result that the multiplication rule would give us. That is, we want to check if we get the same result if we multiply probability of positive times uses drugs given positive, right? Using the probabilities that we found previously, we also read those off the chart. So the multiplication rule says we're going to multiply these two probabilities together, and if you do, we see that we get, you see, notice the 70 cancels in the numerator and denominator, so we get the same result. Well, this is reassuring, but you might wonder, why do we need to use a multiplication rule if we can just read it off the chart? Well, the answer is that we're not always given the data in tabular form, so we need to use the multiplication rule. And here's an example. You can pause and read through the problem. Part of the issue is to determine what probabilities are given. Well, it's easy to see that the probability of C and M are both given. But now you need to determine, there's another probability that's given as well, and it's a conditional probability. You need to determine whether it's probability of C given M or M given C. So that will be part of your pre-class assignment. And then you're going to use the multiplication rule. Recall that if two events are independent, the conditional probability of B given A is just the probability of B. So this affects the multiplication rule if the events are independent. In this case, you get this form, right? So if A and B are independent, here's your multiplication rule. It's just no conditional probability involved. Recall that's because the fact that event A has occurred doesn't affect the probability of B. Here's your prototype example. Numerous coin tosses are independent. Also, doubling down in games of chance. Sometimes if gamblers think if they've lost so many hands in a row that their luck is really bound to change, the likelihood of winning is increased. Well, that's a fallacy because that separate hands in poker or blackjack or whatever are independent. So simply not true. And we saw that sampling M&Ms with replacement, the outcomes were independent events. Same thing with drawing cards. In general, making a selection, sampling with replacement is going to give rise to independent events. Sampling without replacement, they're dependent. It's very critical to keep these straight and not confuse them. We do have a guideline for when the population is really large relative to the sample size, and that is that we can, if that is the case, we can treat the selections as independent, even though they're actually dependent. Okay, so as a summary, we've looked at the multiplication rule for dependent and independent events. We looked at tree diagrams as a way to analyze and write down the various outcomes with their probabilities and the conditional probabilities. We can read right off the table, if we have the data in tabular form, we can read those conditional probabilities and we can read the AND probabilities as well, sampling without replacement and large sample sizes. So that concludes multiplication rule and conditional probability. These two last videos kind of go together.